So you've seen the headlines, right? AI models with billions, even trillions of parameters. They're getting absolutely massive. But here's the thing. Training them is a nightmare. It's like the bigger we build them, the more they just break. They hit these really weird, frustrating walls. Well, what if I told you the problem isn't the model? What if all this time we've been using the wrong map to train them?
Okay, so here's how we're going to break this down. We'll start with the problems everyone's facing, then dig into why our old methods are failing, and then we get to the cool part, the geometric solution that changes everything. Stick with me, it's going to be a fun ride.
All right, section 1. Let's dive right into deep learning's growing pains. It really is a case of when bigger isn't always better. It feels like a paradox, doesn't it? We pour all this effort into making models more powerful, and in return, they just get harder and harder to train.
So, to get more power, what do? We just throw more parameters at the problem. Millions of them, billions even. Each parameter is like a little knob we can tweak. The thinking is, more knobs means a finer-tuned model. But, and this is a big but, that very complexity, that sea of parameters, is actually the source of all our pain.
And you've probably heard of these headaches before. We're talking about things like feature redundancy, where different neurons basically end up learning the exact same thing. Total waste. Then you've got the classic villains, vanishing gradients, where your learning signal just fizzles out, and exploding gradients, where it goes completely off the rails. Now, we usually treat these as separate issues. But what if they're not? What if they're all just symptoms of one single, much deeper issue?
Okay, this is where it starts to get really interesting. The problem isn't the journey, it's the map. We've been so focused on building better optimization algorithms, like a faster car, that we never stop to ask if we're driving in the right direction. What if the map we're using is just wrong?
Let me give you an analogy that makes this super clear. Imagine you're trying to find the shortest path from New York to Rome. If you pull out a flat map of the world, what do? You draw a straight line, right? Easy. But we all know that's not actually the shortest path, because the Earth isn't flat. The real shortest path is a curve over the surface of the globe. That's exactly what's happening in deep learning.
So let's put some official names on this. That flat map, that's what we call Euclidean space. It's the simple, straightforward world we thought we were living in. But the globe, the real curved surface where all the valid solutions actually exist, that's something called a Riemannian manifold. It sounds complicated, but just think of it as the right map.
And this visualizes it perfectly. The Euclidean path, the one from the flat map, tries to take this impossible shortcut. It keeps falling off the true surface where the good solutions live. But the geometric path, it respects the curve. It stays on the manifold and finds the actual shortest path. It's smarter.
Okay, so now we know we're on a globe, not a flat map. That's a huge step, but it also means we need new rules for this new world, right? We can't just use our old navigation system. We need something that understands curves. So, this idea of a Riemannian manifold, let's break it down. Think about standing outside. The ground looks flat, doesn't it? But we know if you zoom way, way out, you're on a giant curved sphere. That's the essence of a manifold. It's a space that locally looks flat, but globally it's curved. And this is the perfect home for model parameters that have to obey certain rules or constraints.
And since we're on a curved surface, a straight line isn't really a thing anymore. The new straight line is called a geodesic. It's just the shortest possible path between 2 points while staying on the curved surface. This is the path we want our optimization to follow.
So how do we actually, take a step? How does the update work? It's actually a really clever three-part move. First, we do what we always do. We calculate the gradient in the normal, flat Euclidean space. Then, and this is the key part, we project that direction onto a tiny, flat plane that's just touching our current spot on the globe. This tells us the correct local direction to move. And finally, we take a step along that path and then kind of pull ourselves back onto the curved surface. So we're still using our old gradient tools, but we're adapting them for this new curved geometry.
Okay, if you thought that was cool, get ready. Because this is where things go from clever to like magic. This whole geometric thing isn't just about finding a slightly better path. It can literally change the landscape itself. It turns mountains into molehills.
And this quote here really nails it. These researchers talk about uncovering hidden convexity. That phrase, hidden convexity, is everything. It's about finding simplicity in problems we thought were impossibly complex.
Just look at the difference. The view on the left? That's what the problem looks like on our flat map.
It's this jagged, ugly, non-convex mess with tons of local minima, all these little traps for our optimizer to get stuck in. But on the right, that's the geometric view. It's a beautiful, simple, convex bowl. There's only one minimum, and it's easy to find. Just roll downhill.
Now, here is the million-dollar question. What if these are not two different problems? What if they are just two different views of the exact same problem? And, yep, that's exactly it. They are the same problem. All that complexity, all those jagged peaks and valleys, it was an illusion. It was a distortion created by using the wrong map. When you look at the problem through the right geometric lens, you see its true form. It was simple and convex the whole time. This magical property is called geodesic convexity, or G-convexity for short.
I mean, that's a massive aha moment, right? So let's take this out of the realm of theory and see how it actually works in practice, from theory to training.
And it's not just one niche application. This pops up everywhere. For convolutional neural networks, using the right manifold can reduce that filter redundancy we talked about. For recurrent neural networks, it's the secret to stopping those vanishing and exploding gradients. Even for graph neural networks, it helps them understand hierarchical data. It's like every type of model has its own perfect geometric map waiting to be used. Let's zoom in on RNNs, because it's such a perfect example. The whole stability problem comes down to the weight matrix W. If its norm is bigger than 1, gradients explode. If it's less than 1, they vanish. But what if we constrain W to live on a special manifold where its norm is always exactly 1? Well, then the problem just goes away. Gradients stay stable. It's that elegant. So hopefully you can see this is way more than just a clever trick. We're talking about a whole new optimization landscape. It's a fundamental shift in perspective. It's like putting on a pair of glasses that lets you see the true shape of the world for the first time. All right, so let's boil this all down. What are the key takeaways? Number 1, the geometry of your problem isn't just some abstract math thing. It matters a lot. Number 2, by respecting that geometry, we can turn really nasty, constrained problems into much simpler, unconstrained ones. And number 3, and this is the big one, this approach can reveal that hidden convexity, proving that problems we thought were impossible are actually totally solvable. This really is a new way to think about optimization.
And that leaves us with a pretty exciting final thought, doesn't it? If many of the most frustrating, long-standing problems in deep learning were really just illusions, artifacts of using the wrong map, it just makes you wonder, right? What other unsolvable problems out there, in AI or any other field, are just sitting there, waiting for someone to come along with the right map?